Sweet. Today's problem is construct a binary tree from preorder and inorder traversal. As you might guess, this is another binary tree problem. And I think this is our last medium. We'll hit some hard problems tomorrow, but this one is pretty challenging, I would say. You kind of have to know a little bit about a lot of things that go on with trees, and then I think it's pretty tricky to set up. So this is one of the tougher ones. I'd say it's maybe a little tougher even than tomorrow's problem, but yeah, we'll take a look at it, we'll diagram it a little bit, and then hopefully I can get through the code smoothly. No promises, but we're gonna see. Okay, so let's take a look at the prompt. It says you are given two integer arrays, preorder and inorder. Preorder is the preorder traversal of the tree. Inorder is the inorder traversal of the tree. And both arrays are of the same size and consist of unique values, so we don't have repeated nodes throughout the tree. And since preorder and inorder are for the same tree, they have the same number of elements, right? One for each node. Okay, just before we move on here, just to remind you, preorder, when we talk about preorder traversal, we're talking about a traversal where we always handle the left subtree, and then the node, and then the right subtree. Sorry, actually, let me back up. That was inorder traversal, is left subtree, self, right subtree. Preorder traversal is self, left subtree, right subtree. Okay, so in this case, because we're looking at a, you know what? I'm pretty sure it's a binary search tree, but they did not specify that. Yeah, I'm pretty sure it's supposed to be a binary search tree here, although that doesn't super matter. What this means overall is basically that the smallest things for inorder will get handled first, and then the middle things, and then the larger things. Whereas for preorder, we'll get whatever's in the middle, followed by the stuff on the left, followed by the stuff on the right. Okay, so we'll have different orderings. They'll be internally consistent, but they'll be usually different from each other just, by virtue of the fact that they've got different logic. Okay, so what we'll do for the examples here is we'll go ahead and, since we're given the tree, we'll go ahead and just talk through how we get the preorder and how we get the inorder traversals. And then we'll talk about some traits that allow us to reconstruct the tree from this information. So for this tree right here, the preorder traversal, again, is when we handle the self node, and then the left subtree, and then the right subtree, and this is repeated for every node. Okay, so for example, for this one, in preorder, we start at the root, we immediately process the root, so it gets added to the list here. And then we move on to the left subtree. So in the left subtree here, we immediately process the node, 2, and then it has no children, so nothing gets added, but now we have exhausted the left subtree, which means we move on to the right subtree. For this node, the same thing happens. We add the self node, 3. We add the left subtree, which is nothing. And then we add the right subtree, which is 4. And then again, left subtree, and then right subtree. So every time we hit a node, we immediately process the node. And then the next thing we do is handle its left subtree. Okay, so for this one, we just get 1, 2, 3, 4. For the inorder traversal, and so actually, this goes against my earlier statement. This is actually not a binary search tree. We won't need that property, but so for the inorder traversal, again, we do the left subtree and then the self node and then the right subtree. Okay, so starting from the root, we don't handle it immediately. We start by saying, hey, if there's anything in the left subtree, handle that first. Okay, so we go left. And we ask the same question. If there's anything in the left subtree, handle that first. Okay, there's nothing there, so now we can process the self node, 2, which you can see is in the list here, and then handle the right subtree. There's nothing there, so nothing happens. Okay, now that we've handled the whole left subtree, we can process the self node, 1, so that's the next thing to go into the list. And then now we begin handling the right subtree. So for this node again, if there was a left subtree, we would do something there. There's not, so next is 3. And then now we handle the right subtree. Nothing in the left, so now we handle 4. And then nothing in the right, so we're done. Okay, so that's how we get the ordering 2, 1, 3, 4 here. All right, now what I want to point out here before we move on is that for the preorder traversal, since the whole nature of it is that we always see the root first, the first element in kind of the overall list here is going to be the root, right? So, for example, on this one, the root value is 1, and we know that that's the case because the preorder traversal always starts with the root. Okay, and then in the inorder traversal, we're going to handle a whole left subtree before we get to the root, right? Which means if we count all of the things to the left of 1, we know the size of the left subtree. Okay, and then we can repeat that. Now that we know that the size of the left subtree is 1, well, if we move on, this is now the first element of the left subtree, and since we found out from over here that there was only one element, we know that this actually is the left subtree. And then right after the left subtree is the right subtree, and we can kind of repeat this process over and over and over again. Again, the first number in each section is the root of a subtree, and then we can go to the inorder traversal and get some information about the size of that subtree. Okay, so that's going to be the overall process here. It's a little bit tricky. We'll go over it in more detail in a diagram in a sec. Let's just take a look at the other example and the constraints here. So this is actually a great example for us to look at here. Preorder and inorder are both just one element consisting of 1. And since it's only one element, it's trivial to construct the tree. It's just a node and that's it, right? And this is actually a great base case for us if we're looking at, so similar to the previous problem, if we're looking at a node and the size of the tree stemming from that node is 1, then we know how to construct it. We just make the node and then we're done, right? So we'll handle that, or we'll treat that as a base case here. And then the constraints, the length of inorder is between 1 and 1,000, and that's the same as preorder. So both of them will be between 1 and 1,000, and they'll be the same. And then the values will be between -1,000 and 1,000. Again, that's not a huge deal to us. We won't really be manipulating them at all. And this isn't even a binary search tree, so we won't really be comparing them either. Okay, so let's see if I can actually diagram this. We're gonna find out. It makes sense in my brain, but saying it out loud and actually diagramming it can be a little tougher. So let's try this out here. I'm gonna make a slightly larger tree than the example they gave us. Doesn't really matter the values here, but we were told that the values will be unique, so we don't have to worry about like duplicates anywhere in here, which is great news for us because that would make it a lot tougher. So here's what I'll do. I'll say, let's go ahead and fill the first layer. I'll say like 3, 1, 2, 4, maybe over here. We'll put like a, I kind of want, well, okay, we'll keep the left subtree pretty small. I'll put 6 and 7 over here. And I'll put 5 maybe right here. Okay, I think this should be sufficient for an example. We're going to see if I inadvertently introduced some annoying patterns. I guess we're going to find out. So let's say that this is our tree. We'll start by doing the... which order do I want to put this in? Preorder first, I think, and then inorder? Yeah, we'll do preorder first and then inorder. Okay, and I'll abbreviate these P and I. Okay, so for the preorder traversal, again, every time we hit a node, our job is to handle the node, and then handle its left subtree, and then handle its right subtree. So for preorder, the first thing we're going to see is 3. In fact, I'll give ourselves a little bit more space here. 3, and then we go into the left subtree. As soon as we do that, we process the root, 1. And we need to complete, okay, yeah. So actually, let me do this. Handle the root, we go left. Handle the root, go left, so 4. Okay, so we handle that root. We're gonna try and go left. There's nothing there. We're gonna try and go right. There's nothing there, so now we can rewind to this guy. In fact, I feel like there's got to be a better way to do this. First of all, let me think about this. I'm going to color code this. So I'll do the preorder in red, and I'll do the inorder in blue. Okay, and what I'll do here is I'm going to mark like left, right, and self just to indicate to us like when we've completed something. So when we do the preorder traversal here, the first thing we do is handle the self. So 3 goes in the list. Okay, and now we're going to begin handling the left subtree. So we go this way. Okay, we're going to handle the self by plugging 1 into this list here. And now we're going to handle the left subtree. Again, handle the self. Handle the left subtree, and the left subtree finishes because there's nothing there, right? Okay, now we're going to handle the right subtree. Nothing there, so we're good. And now that 4 node is completely handled. It's never going to be revisited again in this preorder traversal. So we wrap up by 1 level. We've already handled the self and the left subtree here, so now it's time to handle the right subtree. There's nothing there, so we're done with that. We again wrap up 1 more time, and now we can start handling the right subtree all the way up here. Okay, again, on this 2 node, we're going to handle the self first, and then handle the left. So we hit 6, again, handle the self, and then handle the left. Nothing there. Now we'll handle the right. Nothing there, so now we get to go back to this guy and start handling its right subtree. Okay, so we get to 7, self. Now we'll handle the left subtree. Again, we get here, self. Nothing on the left, nothing on the right. So we can wrap up 1 level. Now we get to handle this guy's right subtree, and we're done. Wraps all the way up, and then you can see we've done self, left, and right for every one of these nodes. Okay, so the order is obviously important, but this is the preorder traversal that we get. And then now we're going to do the same thing, but as an inorder traversal. Okay, remember the inorder traversal is left, and then self, and then right. Okay, so we say, hey, let's go ahead and handle the left subtree. We get here, and we go, hey, got to handle the left subtree. We get here, we go, hey, got to handle the left subtree, but there's nothing there. So now we get to handle the self. So the first thing to go into the inorder traversal here is going to be 4. No way, Dave Winter? I love that guy. Okay, so first thing to go in here is 4. Okay, and then, so we did left, we did self, we do right, there's nothing there, so we're good to wrap up. We go to the previous level. Well, now this guy's whole left subtree is handled, so we're ready to handle the self, which is 4. And now we've done the self, so we're ready to do the right subtree. Nothing there, so again, we wrap up with that node. And then now we're up here. We did the left subtree, so now it's time for the self, which is 3. And now we got to start doing the right subtree. Okay, we get to this node. Before handling myself, I got to handle my left subtree. And once again here, before handling myself, I got to handle my left subtree, but there's nothing there, so now I can begin processing myself, which is 6. And now that I've handled the self, I can start doing the right subtree, nothing there. So we wrap up by 1 level. 2 had its left subtree completed, now we can do the self, which is 2. And now we go right. Okay, I'm gonna like rush through the rest of this because I want to start explaining the actual algorithm here. This is just the traversals. So this is just the prerequisite knowledge to do the problem, right? Unfortunately. Okay, so we go over here. 7's turn now, do the left subtree first. Okay, 5's turn, do the left subtree first. And now that we've done the left subtree for 5, we can do the self. And now we can do the right subtree. Wrapped up to the 7. Okay, so handle yourself. And then now handle your right subtree. And now you can see, once again, we've exhausted the whole tree just in a completely different ordering. So again, the preorder traversal is going to handle the self first. The inorder traversal is going to handle the left subtree and then the self node. And so on and so forth for every single node in the tree. Okay, and at this point, we've done both traversals, and these are the lists that we're going to get, right? And our job is now to take these traversals, and now we'll pretend basically we have never seen the tree before, and we have to figure out what was the original structure of the tree. Okay, and you'll notice again, same number of elements, same constituent elements, no identicals, right? We have to take these numbers and figure out, well, there's hints throughout this that are going to help us reconstruct the tree just from the orderings. Yeah, right, exactly. Easy stuff. Very straightforward, very intuitive. The design is very human. Okay, so here's, I think, one of the really big insights again, is that in the preorder traversal, since we always handle the self or the root node before the left and the right subtrees, this means that the first element here is guaranteed to be the root of the overall tree, right? Okay. And then here's the other piece. If we can find that same element in the inorder traversal, that will tell us what the size of the left subtree is, and it'll also tell us what the size of the right subtree is. It won't tell us how those two subtrees are like constructed, but it will tell us just how many there are. And so now if we know that there's two elements in the left subtree, then we know that this right here in the preorder traversal is the left subtree, and that this right here in the preorder traversal is the right subtree. So one of the conditions for the problem is that there's not duplicate values here. Yeah, so if there were 2 3s, that would be a huge problem for us, unfortunately. So yeah, one of the constraints is just that there won't be duplicates, which means if we find the number, we know that it's the right one, or it's the node that we're looking for. Okay, so what this does for us is it breaks the list down into a root node, which we can construct immediately, and then a left and a right subtree, right? And we can continue this basically until we have a section that is just like one node, or maybe no nodes even, which we'll see in a sec. Okay, so now that we know that this is the left and the right subtree, we can now repeat this process just for the left subtree. So basically, we just pretend we're just looking at this as our list, and we're going to try and figure out, hey, how do I construct the left subtree here, right? Okay, well, if we were just dealing with these two and we knew that this was the preorder traversal up here and this was the inorder traversal down here, we can make the same conclusion, which is, hey, the first thing that we see in the preorder traversal has to be the root, right? Okay, and not only that, but, okay, so actually, let me, just for the sake of clarity, I'm going to kind of redraw this over here. So to construct the left subtree, it's kind of like we're dealing now with the sublist, which we can literally do. If we decide to use list slicing, we can literally say, hey, new list, this list has 1 and 4 for the preorder, and this one has 4 and 1 for the inorder. Okay, so it's kind of like this is the left subtree. Okay, again, same logic as before. We can say, hey, since the preorder traversal always leads with the root, we know that this is the root. Well, if we find it over here, then we know now that the left subtree has 1 element and the right subtree has 0 elements. Okay, what does that tell us? Well, it tells us that this right here is the left subtree, right? And let's just verify that here real quick. So 1 and 4 should be the left subtree. And then in that, 1 should be the root and 4 should be the left child. And you can see that is actually the case here. Okay, so we're just taking the lists, kind of partitioning them, segmenting them into smaller pieces, and then seeing if we can use that information to reconstruct smaller and smaller parts of the tree. Okay, speaking of which, now we can say, hey, the left subtree of this guy has a preorder traversal of 4 and an inorder traversal, oh, sorry, this should be in blue, and an inorder traversal of 4, now that it's just one element, we actually know what this tree looks like. It's just the node 4, right? And so what we'll do from like a recursive like layering standpoint here is we'll make this node. So we'll construct tree node with value 4, and we'll pass it back up to this guy because we know that that's supposed to become its left child, right? Okay, on the other hand, for the right child here, we have a preorder traversal of nothing and an inorder traversal of nothing. And this tells us that it's just, there's nothing here. We can return none. And you can see this is starting to become the exact structure of the tree. We have the 4 over here. Now that we know what this all looks like, or we're done with both subtrees here, we can now construct like the root node over here. So this is tree node 1. Well, actually, here's what I'll say is it's, I think the class definition here says that tree nodes are like, value and then the left subtree and the right subtree. So we can say that this is going to be like tree node 1. This is not really how it works because we'll need the actual node, but I'll say like 4. Right, it's whatever I got back from the left recursive call here. Okay, and now this node is done, and now we can pass it way back up to the root, and in this case, we know that, well, now we've got to do the right subtree, which is unfortunately a lot more extreme here. This is taking a long time to explain. I apologize, guys, but it's a lot of details. I don't know what to say. And that was just for like 2 nodes. We're not even done with the 3rd node yet. It's crazy. Okay, I'm going to see if I can rush through this. I'm going to explain a little bit less as I go, but we're basically going to repeat the same process here. We're going to say, hey, let's go ahead and use this section over here to do this with the right subtree. The preorder traversal is 2675. The inorder traversal is 6275. The root of this subtree is 2. The left subtree has a length of 1, and the right subtree has a length of 2. So these are our left and our right subtrees. And we do it again. So over here, preorder is 6, inorder is 6. Okay, it's just one single node, so we know that we're done. We can return now a tree node with value 6. Now we'll do the right subtree over here, and this one has 7.5 as its preorder. It has 7.5 as its inorder. And that means that 7 is the root. The left subtree is nothing. The right subtree has 1 element. And we'll break it down just a few last times here. I'm running out of space, unfortunately. Let me slide this over. I think that should be enough. Okay, so finally over here, empty preorder, empty inorder. We'll go ahead and return none right here. And then over here, preorder is 5. Inorder is 5. So we can return a tree node with value 5. Oh God, I'm out of space. Tree node with value 5. Okay, so now that this node has both its left and its right subtrees handled, we can now construct the node for that guy, which is tree node that has a value of 2, which was the root, right, that we got right here. Left subtree that comes from here. Right subtree that comes from, oh, you know what? Hold on, I know, I skipped a layer. This is so sad. we're not ready to do that one because we forgot to do this one. So this guy is gonna be a tree node with value 7 that has none on the left, 5 on the right. This guy is now going to be a tree node with value 2 that has 6 on the left, 6, 7, and 7 on the right. And finally, now that we've got the whole left subtree and the whole right subtree done, we're ready to construct the root. This is going to be a tree node with this guy on its, or it has a value of 3. It has this guy on its left, and it has this guy on its right. And finally, we're done. Holy Jesus God in heaven, that was a lot. That was a lot. But this is the core of it, is we can basically break the list down into subtrees. And the eventual base case is we've got just 1 node left or 0 nodes left. Those are very easy to construct. And then we just pass them upward so that the tree gets built kind of from the bottom up here. And you can see that the structure we've got matches the overall structure from when we diagrammed this at the beginning. Oh, crud. Wait, what did I mess up here? Oh, no, I got it wrong. This right here, I wrote it down wrong. That's so sad. I wrote 5, 7 here, and then I wrote 7, 5 right here. I was like, wait, this doesn't match. Oh, that is so sad. Okay, and we haven't even started coding this shit. Okay, let me just correct the diagram. The logic is still all correct. I just put these in the wrong places. So this will be 5, 7 right here. This will be, I'm gonna change this. So this is the left subtree. So that means these go over here. And these go over here. I apologize if you thought that I was doing something right here. I apologize. And this should be 7, 5, none. Man, I really messed up a lot of things here just with that small mistake. Okay, and then everything from here is good. Okay, so yeah, the logic's still the same. Yeah, you can see that there should be a 7 and then a 5 on the left and then a none on the right. And yeah. But yeah, that's a good point. Catching it is actually a big deal. You will make mistakes. Catching it is a good place to be in. All right, so that's the overall algorithm. We're going to do this pretty much in the exact way described here. How do you know? We're going to do it pretty much in the exact way described, and then we'll go back and try and optimize some things. There's a few quite, I don't want to talk about it. There's a few quite easy optimizations, and then there's a few that are like, oh, that's actually hideous and evil and terrible. So I'll split screen this just because I think I'm going to forget what we did. Put you over here and close this here. Let's try it out. Okay, so to build a tree, what do we have to do? Well, if we have its preorder and its inorder traversals, we have 2 base cases. One of them is that it's an empty list. So if not, I'll just say if not preorder, because if it's not preorder, then it's also not in order, because they're always going to be the same size list. So if not preorder, then we can return none. And if the length, well, okay, we don't even technically need this, because we can just say, like, we can let the single node base case be caught by, like, this situation here. Let me think. But otherwise, where are we going to put... No, yeah, okay. I was going to say we could say... And, okay, we'll do it as diagrammed, and then we'll talk about, like, why we don't actually have to do this. I'll say if the length of preorder is 1, then now you can just return a tree node that has value preorder 0, so the first element in that list, and it will automatically have none and none as its left and right child. So this is saying, hey, we have a subtree that only has 1 node. Go ahead and just construct it and return it. We technically don't need this extra base case, but not a real issue to have it either. Okay, so assuming we didn't hit one of the base cases, then how do you do this? Well, the first thing you need to do is say, hey, I actually know or I need to find where the root is, I know that in preorder it's the first element, right? So I'll say root index equals. Now, we could do a for loop to find the index here. I just so happen to know that there is an index function that will just do that, and it'll make it much cleaner. So I'm going to do that. And I think the syntax is inorder.index preorder 0. So this is saying, hey, I know that the root of this subtree is the first thing in the preorder list. What is its index in the inorder list? Because if I know that, it'll tell me how many elements are in the left subtree, right? So if I know that the index is 2, that tells us that the left subtree is 2 nodes, right? So in fact, let me not even call this root index. I'll call this like left subtree size. Okay, so why is that helpful to us? Well, now we can begin to process the left subtree. So I can say now self.build tree. And what I'm going to do, just to line up with the logic that we used in the diagramming here, is I'm going to send in the recursive call here a slice of preorder. And the slice that we want is from the beginning of the list up till, well, here, I'll say this, preorder 0 to left subtree size. And so this is just going to say, hey, go ahead and get elements 0 and 1, but stop at element 2, which is exactly what we want because that's the root, right? It's not part of the left subtree. Okay, so this is saying go ahead and build the left subtree. And I'm going to store that. So what we're eventually going to do is return like the root of that subtree. I'm going to store that as left here. Okay, now assuming we can build the left subtree, what do we need to do? And now we need to construct a, oh, well, actually, hold on. We also need the root of the right subtree. So I'm going to say now right equals self.build tree. Oh, I forgot to pass. Hold on. This isn't correct. This isn't correct. I forgot we need the preorder and the inorder lists here. So let's back up for just a sec. Left is going to be self.build tree. And we need to pass it. Okay, so it's going to be preorder from 1 until left subtree size plus 1. Okay, so this is saying start from the second element and get everything up till here, basically. So like count over by 2 elements. And like, it's exclusive on the right end. So we disinclude this element. This gets us everything from the second element to the end of the left subtree, right? Okay, and then for the inorder traversal, we actually just send it 0 till left subtree size, which is the same logic as earlier. Okay, and now we're going to do the same thing on the right subtree. It's just a little bit more complex here. So we'll call build tree again. For the preorder traversal, we're going to give it, we're going to basically pick up from where we left off here. So left subtree size plus 1 up until the end. So actually I can just leave it like that. And then for the inorder traversal, it's going to start from the element right after the root. So this is going to be left subtree size plus 1. And then it goes to the end as well. Oh boy. Oh boy, oh boy, oh boy. And then now that we have the left and the right subtree, we can construct a tree node that has the first element, so the root, the first element of preorder's value. And then it has left as its left subtree and right as its right subtree. Oh, mama, I hope that works, because if not, I'm going to cry. Let's take a look. Let's take a look. Oh. First try is crazy, you guys. I really was like, I definitely fucked something up. But that's great. Feels good. Okay. Yeah, I'm actually, this is fantastic. I was really worried about this one. There's so many tiny things that can go wrong in this problem, so I'm really glad that worked out. But we're not done. Let's talk about time and space complexity real quick. Although, okay, here's what I'll say. Well, let's talk about time and space complexity. One of the real big problems with this is we keep slicing the lists, and every time we do that, we have to generate a new list, which is a pain in the butt for a few reasons. One is that we're storing all this extra stuff on top of the recursive calls. The other thing is, what was I going to say? A lot of extra space because of the recursive calls. And we're storing extra numbers. Oh, and then also when we create these lists, the only way to create them is to copy them over one by one. Like when we make this list over here, the 1, 4, I have to copy over the 1, I have to copy over the 4, I have to copy over the 4, I have to copy over the 1. So like this is really trashing our time complexity just from constructing so many lists, right? The actual recursion, it's just one thing to do each time, right? Or at least when we get to the base case, it's just make a node, right? But it's a lot of extra memory, it's a lot of extra time. I am having a hard time even thinking about what the time complexity is here because it just depends on so many things. I think it's probably something like n log n, because because you've got to like copy elements from the list and you're doing that log n times. I think it's if somebody is watching this in the future and wants to correct me, I would love to hear it because I frankly don't know. There's a lot going on here. Not to say that the people here right now can't correct me, but I'm just saying is a lot happening. And we would like to be able to not have to copy things from the list. And then here's the other thing that I sort of like glossed over is this index function right here is also pretty slow because we have to look through the whole damn list just to find where the root is. We'd like to like not have to do that, right? But here's one of the other problems that kind of ties these things together is because we keep slicing these lists, the index of the root like changes and changes and changes. Like over here, the index of 3 is, or the index of 4 is, okay, hold on. Over here, there's got to be a better way to do this. Over here, so in the right subtree, the index of 6, right, is 3. But as soon as we go over to this slice, it has an index of 0 all of a sudden, right? Hey, thanks, Dave. Appreciate you. So as soon as we move over to the right subtree, all of a sudden the index has changed. Pain in the butt, like we don't want to have to do that. So what we'd like to do, and I don't know if I'm going to be able to pull this part off, we're going to see, is we'd like to be able to not have to like pass a whole slice of the list. We'd like to just be able to like pass indexes and just say, hey, this is the section you're looking at. Yeah, so that way we just, the list exists in one place. We don't have to like repeatedly reconstruct it. We can just pass indexes to say, like, instead of passing a slice, we can just say, hey, here's the section that you're working with. It goes from 1 to left subtree size plus 1, right? The other thing is if we do that and we just pass indexes instead, we're always working with the original list. And if that's the case, all the indexes stay the same all the way throughout the problem, right? Which is helpful to us because that way we can just use something, well, especially because these are unique, we can just use like a dictionary or a map to figure out what the index of 3 is, for example, without having to look through the whole list, right? Okay, so those are like the two main things that we want to fix. Unfortunately, to fix them, we're going to have to use like a helper function, because otherwise like we're forced to kind of keep passing the list over and over again. Actually, you know what? No, the list isn't a huge issue, because if we pass, so what we're doing here is we're constructing a new list and then passing it, right? if we just pass preorder and inorder over and over again, then that's like kind of fine. Because we're just passing a pointer. It's like fairly cheap to do that, right? Okay, so either way though, we need a new function where we can pass indexes as well, right? So I'll say like definition build tree bounded and gagged. What? Okay, so what are we gonna pass? I'm gonna say let's pass the preorder and inorder lists still. I'll call them P and I. And then let's also pass the indexes for each list. So I'll say the low index for preorder, the high index for preorder, the low index for inorder, and the low or the high index for inorder. Okay, so in that case, a lot of this logic is going to migrate over here, including like the base case. So now we aren't going to be able to use a list length because it's always the whole list that we're dealing with. But instead, we can just say something like if. So how would we capture this? This would be. Okay, if the two indexes are the same, that's a one element list, right? If the. Okay, yeah, so let me actually write that. If P low plow equals, there's so many innuendos here. So if P low and P high are the same, then we have a single element. We can return the node, and I'm going to arbitrarily, well, actually no, I'm going to arbitrarily pick this. It could have been P high as well, it doesn't make a difference. So if that's the case, then having no elements is when P low is greater than P high. So in that case, we can return none. So that's like analogous to these guys right here. Okay. Oh boy. So this part right here, like I said, we would like to optimize this where we can just look something up in a hash table. What I'm thinking about is how can we pass that? So we don't necessarily need to pass it, actually. It doesn't change. So you know what we could do? Well, okay, let me think about this. Let's not even do this. We don't need to do P and I here. We can just say, we don't need to pass it is what I'm saying. Over here, instead at the beginning, we can say like self.p equals preorder and self.I equals inorder. So we're going to store them as part of the class here. And then, so in order to have a hash map that's accessible to the build tree helper function, I'm going to say self.inorder map, because we need to find the indexes of these guys, not these guys, is going to be an empty map. And then we can go through the elements of inorder. Oh, we need the indexes too. So I'll say for I in range, len inorder. Inorder map. Okay, so we're going to look up a value and figure out its index. So inorder map, inorder I. Oh, self.inorder map, inorder I equals I. Okay. We need to duplicate this logic up here. So we'll get to that in a sec. And then when we're done, we're no longer going to do this. We're going to call the helper function with This is the whole list. So 0 to length preorder -1. And then 0 to length inorder -1. Okay, I'm going to say we don't need this anymore. Actually, I'm probably going to open it back up in a sec. Anyways, guys, this is taking forever. It's taking forever. Okay, let's see how we can duplicate this logic over here. So we already have the base cases. We can get the root value pretty easily because it's just whatever is at p low, right? To get the index, hold on, let's think about this. So, okay, what do we need to find? We need to find like the left subtree's information and the right subtree's information, right? So for the left subtree, where is it? It is whatever the index of the first thing in preorder is, right? Okay. I'm going to try and follow the same logic as before. Left subtree size is going to be... I need to think about this for a sec. It's the difference between I low and the index of p and the index of the root, right? I wish I had like talked through this myself before trying to teach it. Maybe we don't even need to do that though, because here's what I'm thinking about, is that we already know that the left subtree starts at I low, right? And then the index of the root has to be after that somewhere. Why is my brain not processing this right now? So, okay, hold on. We need to be able to figure out the indexes of the left and the right subtree for both P and I, right? Yeah, you know what? Left subtree size is a good way to do this. To calculate it, we're going to get the index of the current subtree's root, which is at p low, p of p low here, and then take away I low. So this is getting what index the root is at, subtracting I low, because that's going to tell us how many nodes there are between I low and the root. Okay, that seems right to me. Now we're going to do the whole left-right thing. So left equals, so self.build tree bounded. And what are we going to pass it? It's going to be, well, we know that the left subtree starts 1 after the root, so p low plus 1. And then the end, is going to be P low plus, oh man, left subtree size. See, this is where I'm saying like the indexing stuff is the pain in the butt. Like I know what's supposed to happen here, just adding the things up is annoying. I think it's something like this though. Oh, hold on. I'm gonna refer to the diagram again. So like when we did this, the left subtree size was this minus this, for example, which was 2 minus 0. Okay, yeah. And then over here, it's going to be P low plus 1. And then P... Okay, no, yeah. This is saying count over by 2, basically, the first time. So actually, that is what we want. Okay, so that's how we get the sections for the preorder. And then for the inorder, it's the same as before. So this still starts in the same place. And we're going to go all the way up till... Is it just left subtree? Oh, no. It's going to start at I low. So it looks like it's 0 right now because we're dealing with the main subtree, or the overall tree. But it's going to start at wherever the beginning was before, and then move over by the size minus 1. Right, because if you move over by 2, that actually includes the root. Okay, and then for the right subtree, same thing. But this one, this one's going to be a lot more annoying. I'm going to say, okay, so same, it's basically like this, but plus 1 more, right? P low plus left subtree size plus 1, because we want to start 1 over, and then we want to go to the end of the current section. So the end is going to be still P high. Okay, and then, oh, I just wanted a little bit more space there. Okay, and then for the in order section, kind of the same logic. It's going to go, well, it's actually just left subtree size plus 2, right? Oh, no, I'm doing it again. I'm thinking it always starts from 0, but it doesn't. It's just whatever the original... Well, okay, again, we can just do this. Like, find this number, and then move over by 2. So this starts at I low plus left subtree size minus 1 plus 2, so plus 1. And then it ends at I high. Oh, dear Lord. Oh, dear Lord. Okay, and then now we got the left subtree, we got the right subtree. We are going to now return a tree node that has P low as its value, left as its left subtree, and right as its right subtree. Good God. Okay, and this is self.p because we're storing it as a class variable now. My God. Okay, so yeah, lots of index passing here. We no longer need this because we're doing that in the helper function now, and I hope to God that this worked because I don't think I have anything left in me, guys. Self.build tree bounded 0. Oh, length preorder minus 1. Length in order minus 1. Oh, self.p right here. I'm goated? I'm goated? Okay. That took an hour. I'm gonna cry, you guys. That felt really good though to actually get that right. I think I've done this optimization like maybe once in the past, and I knew it was gonna be a pain in the ass. I also thought I was gonna get it wrong, but this time it was just a pain in the ass and I got it right, so it feels good. um, but there you have it. Okay, so just to recap, benefits of this form here: we don't need to copy the list elements over. We don't need to have separate lists get constructed over and over again because we're just referring to an already existing list. And we no longer have the overhead of looking through all of the elements to find the index of the root. We just have it preset for us by using this map right here. Just this is a real pain in the ass. And there's probably a more elegant way to do it, but here we are. It's done. I'm going to call it there because it has been 1 hour and I was supposed to go to the gym. And yeah, so thanks for stopping by, y'all. If you have any questions, please let me know. This is a toughie. But other than that, have a great night. And I won't see you tomorrow because it's Friday, but I'll see you Monday.